What if one day we pointed our most sensitive instruments at a cold, empty patch of space and found something warm staring back at us? Not glowing, not burning, just quietly warm. No star nearby, no radioactive decay we can see, no obvious explanation, and yet undeniably, measurably producing heat. That is the uncomfortable question at the center of the object now known as 3I Atlas. And the deeper scientists looked, the stranger it became. To understand why this matters, we need to start earlier than most people expect. Long before 3I Atlas ever entered a database or earned a provisional name. We need to go back to how we learned to look for heat in space at all, and why, for most of modern astronomy, heat has been one of the most reliable clues we have. For centuries, astronomy was about light. If something didn't shine or reflect, it might as well not exist. That changed in the 20th century, when scientists realized that the universe glows in far more ways than the human eye can see. Infrared astronomy revealed a quieter cosmos, where objects radiate warmth long after their light has faded. Dust clouds glow softly, cooling stars leave thermal fingerprints. Even dead planets leak their last stored heat into the void. By the late Cold War, infrared sensors had become extraordinarily sensitive, driven by missile detection programs and later repurposed for space science. Heat, it turned out, was honest. It was hard to fake. If something was warm, there was usually a reason. A star, a planet, a chemical reaction, radioactive decay, friction, tidal stress. Energy always left a trail. That assumption that heat must come from somewhere became a kind of unspoken law. And like many unspoken laws, no one realized how much depended on it until it was challenged. The first hints of 3I Atlas appeared not as a discovery, but as an anomaly. Automated sky surveys are very good at ignoring things that don't fit expectations. Cold objects in deep space are common. Warm ones are not. In preliminary scans, 3I Atlas was flagged and then quietly downgraded, assumed to be a data artifact or background interference. It didn't move like a nearby asteroid. It didn't pulse like a variable star. And most importantly, it didn't cool down the way it should have. When follow-up observations confirmed the readings, the object was given a temporary classification. The 3I designation hinted at something even more unusual. It appeared to be only the third interstellar object ever identified passing through our solar neighborhood. Unlike typical comets, it lacked a visible tail. Unlike asteroids, its trajectory suggested an origin far beyond our system. And unlike either, it was warm. At first, researchers reached for familiar explanations. Perhaps it was a comet with an unusually dark surface, absorbing and retaining heat. Perhaps subsurface volatiles were sublimating too gently to form a visible coma. These ideas fit neatly into existing models, and for a while they held. But then came the timeline problem. As 3I Atlas moved farther from the sun, its heat signature didn't drop the way models predicted. Solar heating couldn't account for the persistence. Internal radioactive decay would have required a mass and composition inconsistent with its observed size. Tidal heating was impossible. There was nothing nearby to stretch or squeeze it. And yet the infrared glow remained, steady and stubborn. This is where the story shifts from routine science to genuine discomfort. To explain why this bothered astronomers so much, it helps to think of heat like a bank statement. Energy goes in, energy comes out. If money keeps appearing in your account, eventually someone asks where it's coming from. With 3I Atlas, the deposits kept arriving, but every known source came up empty. Some researchers proposed exotic chemistry, slow, energy-releasing reactions unlike anything commonly seen. Others suggested phase changes in ultra-dense materials, releasing latent heat over long timescales. These ideas were clever but strained. They worked only if 3I Atlas was made of substances we had never observed naturally forming in space. More radical voices began to ask quieter questions. Not what is it made of, but what is it doing? This is where speculation entered the room, and everyone became very careful about their wording. No one was claiming artificiality, no one was invoking intelligence, but the language shifted. Papers began to use phrases like non-equilibrium thermal behavior and internally regulated emission. The object wasn't just warm, it was maintaining warmth. Historically, science has been here before. In the early days of pulsars, some scientists half-jokingly labeled them LGM, little green men, because the signals were so regular they seemed intentional. The joke faded once natural explanations were found, but the lesson remained. Nature is capable of behaviors that look designed until we understand them. The question was whether 3I Atlas would follow that pattern, or break it. As observations continued, another strange detail emerged. The heat output wasn't random. It fluctuated, but within a narrow band as if constrained, like a thermostat without a visible heater. That alone didn't imply anything extraordinary, but it forced scientists to confront a possibility they rarely enjoy: incomplete models. The reality is that our understanding of interstellar objects is still young. Until recently, we had never observed them up close. We assumed they would behave like leftovers, cold, inert debris drifting endlessly. 3I Atlas challenged that assumption. It suggested that some objects might carry internal processes far longer than expected, perhaps preserved by formation conditions we haven't yet imagined. Still, there was a line science refused to cross. Public speculation raced ahead. Online forums, headlines, and videos eagerly filled the explanatory vacuum. Was it a probe? A relic? A fragment of technology older than the sun? Scientists responded the only way they could: by slowing down, by insisting on boring explanations, by reminding everyone that unknown does not mean unexplainable. And yet, even within those cautious boundaries, the mystery remained intact. Eventually, as 3I Atlas continued on its outbound trajectory, its signal weakened, not abruptly, not dramatically, but enough to suggest the end of whatever process had been sustaining it. No sudden shutdown, no flare, just a gradual return to thermal silence. Whatever had been happening, it had a lifespan. Which brings us back to the question we started with. Was 3I Atlas producing heat without a source? The honest answer is no, and yes. No, in the sense that physics still demands a mechanism. Energy cannot appear from nowhere. But yes, in the sense that the source was not one we could identify, isolate, or definitively explain with existing frameworks. The heat was real, the measurements were sound, the explanation remains incomplete. What likely happened was not a violation of physics, but a reminder of humility. 3I Atlas exposed a gap between what we assume about the universe and what the universe is willing to show us. It didn't rewrite the laws of thermodynamics, it simply revealed how much room there still is inside them. In the years since, the object has become a reference point, a case study taught not for what it proved, but for what it unsettled. It reshaped how astronomers think about interstellar debris, long-duration energy storage, and the danger of overconfidence in neat explanations. And maybe that's the most important part of the story, not the heat, not the mystery, but the reminder that the universe doesn't owe us intuitive answers. Sometimes it hands us a warm object in a cold place and waits to see if we're curious enough and patient enough to admit we don't yet understand it. Because in science, as in exploration, the most unsettling discoveries are rarely the ones that break the rules. They're the ones that follow them, in ways we didn't expect.